Welcome back to the generative flower tutorial. Today I'll show you how to make the generative flower look organic with noise and bring it to life with animation. This is part 2 of my series where I generate flowers from curves with Blender geometry nodes. In the previous part, I have shared how to generate the base mesh by instancing and warping a lot of Bezier curves. If you haven't seen part 1 yet, please make sure to check it out. Alright, let's dive in. Now let's talk about noise and displacement. In a graph like this, that is not exactly small, we can introduce noise at many points. For example, we could displace the vertices of the petal endpoints that we laid out in the big spiral, or we could displace the curves, or we could displace the final mesh itself. They will all produce organic results in the end, but they introduce different levels of details. For the sake of this tutorial, we will focus on displacing the points on the curves and the mesh. Alright, let's focus on our curves for a second. First of all, we need to give our curves a little more resolution. We did give it more geometry, but it's in the extrusion step. So now if you look at the spreadsheet tab, each spline has exactly 2 points, which is not enough. So let's drop in a resample curve node and resample by length. Now let's drop a set position node, connect the offset to a noise texture node, change the noise type to 4D. This way we can kind of use the W value as a seed of the noise. You can already kind of see the vertices are going crazy, which is great. Now instead of feeding the float factor to the offset, let's feed it the 3D color and drop a map range node so that we can map the value from 0, 0, 0, 1, 1, 1 to negative 1, negative 1, negative 1, 1, 1. This way the offset can go in both directions. Let's decrease the scale of the noise. Alright, this is looking quite nice. There's one issue though, which is the endpoints of the flower curves are now moving off where they're supposed to be. If we get rid of the viewer and connect the output to extrude petal, you can see our petals are not exactly extruding from the center. To fix that, drop in a multiply node. Actually, a scale should suffice. For the scale factor, let's feed in the spline factor. Alright, it seems to be doing the opposite. Somehow it moved the tips to exactly where the outline is, but the bottom is still floating around. Now that means our curves are reversed. Its spline factor is going from 0 at the tip to 1 at the bottom of the petal. To fix that, let's drop in a float curve and map 0 to 1 and 1 to 0. Now everything is in its right place. You can even use the float curve to freely specify how much impact you want for different sections of the petal. For example, I can make it really mild towards the center, but make it really intense towards the tip. Sweet, this is looking smoking hot. Before we forget, let's select all the nodes that we've just added and put it into a group called Displace Curve with Noise. Alright, let's dive in again and build a few controls for the effect. First of all, let's build an intensity control. So after this float curve, let's drop a multiply, connect it to the original output, feed the other factor to the group input, and name it intensity. Let's also feed all these controls on the noise to the group input. So let's expose W, the scale of the noise, the detail, the roughness, and leave out distortion for now. Now, if we slide the sliders around, we have a lot more control from this one node. Let's try to apply this to the leaves as well. Let's go to our gen leaf nodes. First, we're going to do a little bit of refactor. Let's dive into gen leaves. Let's remove the extrude petals for now so that the output is only the raw curves, like this. Go one level up. After the 2 gen leaves, I'm going to use a drawing geometry to join the raw curves together, and then use an extrude petal to get the actual leaf mesh. Alright, let's disconnect the old gen leaf nodes from the final drawing geometry and connect our new node instead. Cool. So let's connect the width on the extrude petal to a group input. Call it leaf width, and let's move it up to go with the other leaf parameters. Great, we have our leaf width control. The reason why we go through all this trouble to do the reshuffle is because now that we have singled out the curves, we can drop a displace curve with noise node right between the raw curve and the extrude petal so that we can move them around before they're extruded. As we tweak the intensity, we notice the same issue that we ran into as the petals, which is the roots are moving the most while the tips are not moving. So this means our curves are reversed. So if you see the same behavior, a quick fix is to use a reverse curve to flip the curve before we feed them to the displacement. Now the displacement works correctly. Alright, our leaves are looking a little blocky, so let's connect the resample length from the extrude to a group input and name it leaf resample length. Let's leave the value at 0.1 for our leaves, and let's also just make the leaves a little narrower. Sweet, that's it for displacing the curves. Now let's move on to displacing points on our extruded mesh. If you think about it, all of our petals are generated by sweeping a petal curve across a central curve, like this. We can easily define a UV coordinate system where the U goes from 0 to 1 along the profile curve, and then the V goes from 0 to 1 along the central curve. With the UV defined this way, we can then use it as the position to generate the noise with. This UV value will also be very useful for applying materials later. Let's build it. Let's dive into the extrude petal. So let's first figure out where the U can come from. So U should be going between 0 and 1 along the profile curve, right? Which is the curve line here. We can't quite see it, but it's going from 1 to -1. So I'm going to drop a store named attribute after resample curve and feed the spline factor as the value. And let's call this U. If you look at the generative mesh in the end, U is there. Now let's do the same for the central curve. So essentially this is the central curve, right? We first resample and then set radius. Now let's drop a store named attribute after the set radius node, then feed it the spline parameter factor. Call this V. Alright, let's go one level up. And after the extrude petal, we can drop in a set position node. We're gonna set the offset to a, again, noise texture field. And change the noise texture again to 4D. Same thing here, feed the color to a map range. Map it from 0 to 1 to -1, -1, -1, 1, 1. Let's again decrease the scale. And for the vector here, we actually want to feed in the UV that we just created. So let's do a combine vector XYZ, and the X would be the name attribute U, and the Y would be the name attribute V. Again, if we want to apply different displacement intensity throughout the flower, you can drop a scale node after the map range. And then for the factor, feed it whatever you want. Here I'm just gonna plug in the center factor, feed it to a flow curve, so that I get a bit of variation as the petals go from the edge towards the center. But feel free to art style them however you want. This step is really optional. Alright, now let's select all of these nodes for displacement and put them into a node group. Call it UV displacement with noise. And let's feed the result to the drawing geometry. Alright, time to build some controls. Let's dive into UV displacement group and make all of W, scale, detail, and roughness a group input, just like what we did for the curve noise. Let's also drop a scale node after the map range and feed the factor to another group input and call it intensity. Alright, we are in control. Well, as we play around with this control, you can notice one problem, which is all of the petals have exactly the same noise patterns. They all kind of have this bump in the middle. This happens because our UV is 0 to 1 for every petal, and we're also feeding the same W to the noise used on every petal. So of course you will get the same pattern everywhere. To fix that, we can simply feed a different W value for the noise for each petal. Connect the W value on the noise to an add, and let's feed it the W from the group input. For the other factor of the add, if I just feed in the ID here, it won't look great because remember, this is computing on the set position for each point, and each point will have a different ID, so you'll get a very noisy result. What we want is a unique seed value for each central spline, and in turn, each petal. Let's go one level up and go to our extrude petal. So in the very beginning, where we have all the input curves, drop a store named attribute, connect its value to a curve index node spline index output. This way we can store the index of the spline that each point is on. Let's call this seed. So if we go to the very end and look at the extruded mesh, there's a seed stored with each point, and it goes from 0 all the way to 182, which matches the number of petal we have. Sweet. Let's go one level up and then dive back into UV displacement. Let's feed the seed attribute we just created to add. Voila, now our petals are all displacing, distorting in its own way. Alright, let's go back up. I'm gonna lower the intensity so it doesn't look so dramatic. Alright, this is quite nice. Let me show you another trick, which is that we can control the noise scale on U and V independently. So if we drop a multiply after the U named attribute, we can use the other factor to either use a noise with a smaller octave or a bigger octave. And this only affects the displacement along the U direction, which is the direction of our profile curve. I'm gonna leave the value at 2 for now. You know, sometimes the petals are naturally wrinkly like this, and from the side view, they look quite bumpy. So what we're doing with noise is a simple way to simulate that effect. Sweet. Alright, let's go one level up. Let's apply the same effect to the leaves. So let's look at our extrude petals for the leaves. We already have UV on the leaf mesh because they're already generated by the extrude petal node. Great. That means we're ready to just drop a UV displace with noise node. And there's our displacement. Maybe a little too much displacement. It looks a lot better when we use a smaller intensity, but when we crank it up, you can kind of see the root of the leaves are flying off from their original position again. Let's go into the displacement node, and right here we're using the center factor with a float curve to scale the intensity of the displacement. But center factor doesn't really exist on leaves, so let's change it to something else. For example, V, which is an attribute that exists for both petals and leaves. Now that's looking a lot better. Let's use a smaller intensity, maybe something like this. Okay, I like it. So there are many more parameters that we can tweak. For example, in the displacement node, we can feed the factor of the multiply to a group input. We can switch between different types of flow curves, but I will leave it to you guys to tweak it. For now, we're done with noise displacement. Yay! Alright, now moving on to part 2 of part 2. Let's build some materials. To begin, let's go to our scene tab, switch render engine to cycles. Select our flower object, create a new material on it, call it flower mat. It's on the geometry node object now, but this won't matter too much because we will actually be setting the material using a set material node. So let's set it on the petals. Let's set the flower material. Now let's go to the shading view and look at the shader network of the flower material. Let's use 2 attribute nodes to get the U and V attributes. Let's double check that UVs are being read correctly. So drop a color ramp node, connect U to it, and connect the output to the shader color. You can kind of see there's a gradient that goes across petals. So that means it's working. Let's change the color to something more saturated, like red. Now let's check V. And okay, as you can see, V is actually going from 0 at the tip, and then to 1 at the center. You can go to the geometry node and reverse the curve if you find this counterintuitive, but for now, let's just run with it. Alright, let's use the combine XYZ to combine U and V into a vector. Drop in a noise texture node, change the dimension to 40, connect the factor output to color ramp. Now we have kind of a cloudy color pattern going on the petal, which is pretty cool. Let's lower the scale of the noise a little bit. Let's also move the color ramp handles closer together so that we get a more obvious transition. And now, as you can see, we kind of, again, get the same pattern on every petal. And this is because UV goes from 0, 0 to 1, 1 the same way for all petals. To fix that, let's duplicate attribute and read in seed, which is different for each petal, but the same for all the vertices on each petal. Let's feed the seed to the W of the noise. Keep adjusting the color ramp handles. And now we get more of a unique pattern everywhere. Alright, let's try out some different colors. Alright, I quite like this color combination. Let's go with that. Let's also go ahead and tweak some other parameters, for example, using fewer petals. Next, let's introduce some bumpiness to our material. Drop in a bump node connected to the normal of the principal BSDF node. And then for the height, we're gonna feed it to another noise texture and use the UV as the vector input. Alright, already you can see there's a pretty intense bump, so let's lower the scale. Let's use a 4D noise. Again, let's feed in the seed. I'm gonna add it with an offset so that we don't get the same noise pattern as we did for the color. Feed the result to W, and there, a unique bumpiness for each petal. Let's tone down the intensity a little bit, and that's the bump. Now I'm gonna duplicate the material and rename it to leaf mat. So if we go to our geometry node, we can drop in a set material for the leaf geometry and set it to leaf mat. If we go back to the leaf material, we can change out the color, the noise, its size, its scale, however we want. I'm just gonna leave it at this color for now. Didn't really put a lot of effort into finding the perfect color, but I think it's looking quite nice. Alright, for stem, we're gonna give it a very simple material. So let's create a new material, call it stem. Go to geometry node, go to this extrude stem, where we generate the stem geometry, and then do a set material, stem. Alright, that's about it for the material. There's a lot more to the material that you can tweak. You can give it a translucency, transparency, but for now we're just gonna keep it simple. I mostly wanted to show off how you can take advantage of the U and V parameters from the generated geometry and create some cool patterns from it. Okay, that concludes the setup for the entire mesh generation and material flow. It was a fairly complex setup, but once you're done with it, this is where the real fun begins. You can freely change up the shape of the curves, tweak them to however you want, change up the parameters. I can spend hours playing around with it, and I did. And once you're happy with the way your flower looks, we can move on to part 3, animations. Let's make some trippy animations, and because we're overachievers, let's also make them loop. So for our animation setup, I'm gonna leave frame start at 1 and end at 240. With a frame rate of 24, we're gonna get 10 seconds in total. If you recall this displace curve with noise node, we have this parameter W, which is basically a seed value that we feed to a 4D noise. So if you slide this W value around, we can basically build a nice, smooth, windy kind of noise animation with this parameter. Alright, I'm gonna crank up the intensity to make it a little easier to see. So for W, if we simply feed in the scene time, seconds, and hit play, it already works, but it does not loop perfectly, meaning the last frame does not smoothly continue to the first frame. So here's the tip for making any animation loop. Conceptually, it's actually really easy. So if you think about the graph, where the x-axis is the normalized time interval that goes from 0 to 1, and the y-axis is the value that you want to animate. You want to calculate your value so that it starts and ends at the exact same value at 0 and 1. For the values in the middle, you can make them whatever you want, but as long as the start and the end are the same, you will get a perfect loop. To play your loop multiple times, you can essentially take your original pattern and then scale it down across the x-axis so that your graph is repeated several times. Alright, let's build this out. For our second, I'm just gonna make it follow a sine wave. Let's first normalize it with the map range node, and let's map it from 0 to 10, 10 being the total length of our animation, to 0 to 1, the unit interval. Next, let's feed it to a multiply, and then for the other factor, I'm going to connect it to a constant value, leave it to 1. This will become the loop count of our animation. Next, I'm going to multiply it by 2 times pi, because a sine wave repeats itself every 2 times pi. Let's connect the result to a sine to run the sine wave through it, and finally connect the output to the W value. And if we play the animation, you can see that we're getting the classic sine wave animation, which goes back and forth, back and forth, back and forth. And the best part is, now it loops perfectly. If we go back to that constant for loop count and increase it to 2, you can see that the motion is repeated twice for each loop. Everything feels a lot faster. If we crank it all the way up to 10, now the back and forth is super exaggerated because it's running it 10 times per loop. Alright, I'm just gonna change it back to 1 for now. This is all well and good, but one thing that troubles me a little bit is our petals are all moving in unison. They all swing back and forth at exactly the same time. To fix it, I want to introduce a timing offset so that for petals that go along the outline curve, their timing is offset based on where they are on the outline curve. Alright, let's see how we can compute this offset. So if we move all the way to the beginning of the graph where we computed the big spiral for the petals, here we're multiplying the ID of petals by 0.38 and then taking the fraction to make them go around the loop. So this fraction is exactly what we want. So after the store named attribute for the tangent, let's drop down another store named attribute for the fraction. Call it curve factor and feed the fraction value to its value. Let's make sure this value is kept throughout the graph. So if we check the node right before the displacement, it has this factor called center factor. So great, we're all set. Alright, let's go back to where we computed the normalized sin time. So right after the map range, drop down and add node. Let's offset the normalized time with our curve factor. Let's connect the output of add to another fraction so that the offsetted value is always clamped between 0 and 1. And finally, let's feed the output to multiply. So if you recall, here we're multiplying the time factor with the loop count. So it's totally possible for its value to go over 1. So let's drop another fraction afterwards. This way we always make sure the time interval we output is between 0 and 1. Let's connect everything together. Now if we go back to preview the displace curve node, play the animation, voila, now our sine wave animation is staggered around the loop. The effect can be quite subtle. You kind of have to develop a sense for spotting where the sine wave is moving along the loop. But trust me, subtleties like this makes a world of difference. Let's build a little control for the amount of staggering that's going on. Currently, our curve factor goes from 0 to 1 for all the petals. If we plug it to a multiply node, we can use the multiply factor to control the amount of staggering. For instance, if you set the value to 0, everything is back to moving in unison. If you give it a value of 0.05, there's a very gentle staggering, and if you crank the value all the way up to something like this, the staggering is so spread out, you can barely see a pattern. It looks like every petal is doing its own thing. For now, I'm gonna leave it at 0.1, something that is gentle but still noticeable. Alright, this bunch of nodes, all the way up to the last fraction, are extremely useful for controlling time. So let's throw all of them into a node group and call it normalized t, because it always outputs a normalized time factor. Alright, let's go into that group again and make a bunch of group inputs. First of all, let's make the total number of seconds an input, call it total seconds. Let's also make the name of the attribute with which we compute the time offset for each element a group input, and call it offset attribute name. Next, for the offset multiplier, we're also going to make an input. Let's call it offset scale. And finally, for the loop count, we're going to get rid of the constant value and instead feed it a group input called loop count. Alright, now we have a node group that is very useful for warping time and controlling aspects of the loop. Alright, let's keep tweaking it a little bit and maybe decrease the intensity of the noise displacement. So that's it for the wave motion. Let's see what else we can introduce. While messing around, I discovered this cool way of animating curves with the trim curve node. So let's drop that in. Now we can kind of use the end factor as the growth point for that curve and the start factor as the vanishing point. So if we simply plug in the normalized t to the end factor, there's something cool happening already. We have a curve growth effect. And even the staggering motion is kept. You can kind of see the growth is delayed for each of the pedal by a little bit. Let's move these nodes out of the way. I'm gonna duplicate normalized t and feed its value to a flow curve. And then feed the flow curve to the end factor of trim curve. Then I'm gonna duplicate the flow curve, feed it the same normalized t, and then feed its output to the start of trim curve. Now, if we tweak the curve for the end factor to accelerate really fast in the beginning towards 1, and then warp the start curve to only slowly increase in the beginning and then accelerate towards 1 in the end, you can kind of get this motion where the flower grows into position really fast, stays there, and shoots outwards in the end. Alright, I'm gonna try to use a different time offset, such as 0.1, so that the offset is not so in sync with the wave action. I'm also gonna adjust the start curve and the end curve here a little bit, and maybe change the loop count to 1 so that everything feels slower and gentler. But really, please mess around with these parameters however you like. Personally, I think this is perhaps the coolest part of the whole tutorial. With a few parameters and curves, you can rather easily change up how this entire complex animation looks and feels. This is really only possible because of geometry nodes. Alright, now if we feed the output of trim curve to extrude pedal, get rid of the viewer, you can now see the flower mesh is coming to life quite nicely. Alright, one thing a little funky with the motion that we can fix. So if you look at the way that the petals disappear, maybe look at these few frames. So you can see that right before they disappear, they still have the full width of the petal. So in one frame, they're still rather big. Yes, they're short, but they're wide. But the next frame, they're completely gone. This makes the ease out effect a little abrupt. To fix it, we can feed the normalized t to another flow curve and basically use this to define the decay of the width of the pedal. So at 0, it's at 1, meaning full width, and then as the time approaches 1, we narrow down the width so that it accelerates towards 1 and then it slows down and reaches 1 in the end. Let's see how we can fit this curve to the pedal width. So right before the pedal width, let's drop in another multiply node, connect the curve as one input, connect the original pedal width at the other input, and feed the output to the final pedal width on the extrude pedal. Let's play the animation. Good. The pedal width smoothly narrows down to 0. Alright, the basic animation setup is done, and it's now time to mess around with the parameters again. So try apply different loop count to the pedal motion. Try out different time offset scales. These tend to have a surprisingly big impact on the final motion pattern. Also tweak the curve, maybe rotate it in 3D along the x-axis or y-axis so that it shows off more aspects of the motion. Alright, I know there's one last thing that we can fix, which is, remember this decay curve that we fed to the pedal width? Let's also feed it to the noise displacement. So plug it into a multiply, Set the original intensity as the other factor. This way, as the petal fades away, it will not be extruding as intensely as when it is fully visible. Alright, now the fade out is silky smooth. Great! So one of the great fun of tweaking these parameters is that you can see the motion in real time. But sometimes when you have a lot of geometry, for example here I have a lot of petals, frame rate starts to drop. To work around it, you can simply decrease the petal count and then go ahead and tweak all the parameters, knowing that you can retain the same feel of the motion when you increase the petal count back up. Another parameter that has a lot of impact on performance is the resample length. So when you want to test out the motion on a heavy geometry, maybe increase the resample length. For example, let's change it from 0.1 to 0.5. Now with even 200 petals, we can run at 24, even more FPS. This is really freaking cool. Then when you render, you can lower the resample length, knowing that the motion will look the same. Now finally, let's bring this animation fun to the leaves as well. So let's go to our displace curve with noise node for the leaves. We want to do the same thing to the leaf curves as what we did to the petal curves. Basically, we can animate the W value of the noise used for displacement with these three nodes. If you want, you can put these nodes into a node group to easily reuse them. Let's call the group animate W because this is intended for the W value of a noise. And now we can drop down the same animate W node here for the leaf displacement. Now let's go into animate W and expose some parameters, for example, the name of the offset attribute, the offset scale, and the loop count. Note that our offset attribute is actually center factor here, which is what we use for the petal. This attribute doesn't really exist for the leaves, so their motion won't really be offsetted. But that's okay, we'll just have the leaves do a simple sine wave together. If you want, you can actually go ahead and compute the offset factor for each of the leaf curves, but for simplicity, I'm just gonna ignore that for now. Alright, we're almost done, minus the tweaking part, which can be endless. One last thing before we end the tutorial, I'm gonna show you very quickly how I set it up a very basic lighting. So I threw in an HDRI image as the world background. The one I picked is a sky texture at sunset. I kept the intensity very low, kind of just using it as a fill light for this entire environment. Next, I created the backdrop, which is a single plane. I really didn't put too much effort into it, but basically I dropped in the plane, scaled it up, and then put it right behind the flower. For the key light, I used an area light. I kind of put it quite close to the flower, a little to the right and pointing towards the left. Also adjusted the intensity and the angle so that I cast some nice soft shadow on the backdrop. Camera setup was also extremely simple. I just had one camera sitting on the z-axis and pointing at the xy plane. I also placed a second area light, used a different color, made it less intense, and pointing from a different angle so that it fills in the area where the key light doesn't hit as much. Okay, so that concludes the final part of this tutorial. I really hope you enjoyed it. I will link the project file in the description. Make sure to like and subscribe if you find it useful. Oh, please also leave a comment down below on what tutorial you'd like to see in the future. I'll see you in the next video. Happy creating, and don't forget to save!